Okay, hello again to everyone. Let's give everyone 1 minute or two to join from the various back-to-back meetings, and then we're gonna get started with the T2TRG session. Okay, now we are 2 minutes past the hour. Let's get started. So welcome everyone. This is the Think to Thing Research Group interim meeting. My name is Ari Keränen, also co-chair Karsten Borman here. Quick reminder about the Notewell. So this is an IRTF meeting, so the usual Notewell applies. Short version is that you may be recorded, and if everything goes as planned, you are being recorded. Also be nice to each other, and the IPR guidelines of the IETF do apply. The longer version of the Notewell is available in the following slides, in particular about the IPR disclosure rules, about the audio and video recordings being public and that you consent to yourself being recorded, and finally about the privacy and code of conduct, in particular, be respectful to each other, and there are links for more information if you need to access that, but you can of course always reach to us chairs for more details. Also, a quick reminder about the goals of the IRTF. So this is an IRTF meeting, and we focus here on long-term research issues that are related to the internet. And then there's the IETF, a parallel organization that has the focus on engineering and standards making. So here the focus is on conducting research, not standards development, although we of course work very closely to various IETF working groups where the standards development often happens, and we exchange information and often ideas between these two groups. Quick administrative. So we have notes in the Etherpad as usual. You have the link there and also in the GitHub page and in the data tracker page. I will be taking in notes, but also appreciate if you can chime in there. And I already see there people helping. So thanks a lot, Marco. Also, you can join the Meetico via Tulip using that link on the center. And if you're not already at the mailing list, please do subscribe. That's where you get always the latest information about the meetings and other activities. And finally, we have the link to the GitHub repository as usual, where you'll find the latest draft agenda and other meeting logistics. Quick note on the upcoming meetings and activities. So this is one of the online meetings that we have usually between IETFs. So what we are planning to do, this one is focused on security topics, which is one of the major topics we have at T2TRG. The other major topic at right now is data modeling. So we're planning to have an interim meeting focused on data modeling topics, perhaps sometime before summer, and then have a face-to-face meeting at the Madrid meeting at IETF 123, which we plan to be again more a summary meeting, a bit higher level and of the various activities, whereas here in the interim meeting is perhaps a bit more towards progressing the work. Then our agenda for today. So we have from Carolina a presentation on the topic of why is my smart home still dumb? This is actually a rather broad topic, and Carolina has been doing quite detailed research on that. We planned here a teaser version of a presentation, and then in the Madrid meeting to go a bit more details on the topic. Following that, we have from Carson a report from the IETF 122 that just happened, and especially on the security discussions that happened there. After that, we have update from Mohit on the terminology and processes for initial security self for IoT devices draft. Followed by that from Michael Richardson, a draft update on the taxonomy on trust anchors. And finally, from Christian Amsus, a presentation on the ray time validating token expiry on an unbound local time interval. There's also a draft on that, with bit more earlier work than the ones from Mohit and Michael. And then finally, if we have time, we'll have a few minutes for Chair's wrap up. Any questions or comments on the agenda? Okay, if not, then I think we are well on time. Let me set up the slides for you, Carolina.
Thank you.
And
so for the control, do I ask for the slides as well, or
now you should have
okay?
some.
I see. Yeah. Okay. Got it.
Oh, thank
Just
you.
had
Please
to
go
press
ahead.
the right button. Sorry.
Right. Thank you so much for letting me speak. So my name is Karolina Skrzywanko. I'm currently doing a PhD at UCL, and my topic of interest is building automation, which is what I would like to talk to you about today. So for the purpose of this talk, I will avoid the complications of industrial building automation and will focus more on the IoT side of things, which I think is what most of you are familiar with. And indeed, I think a lot of people in this group probably have experience with running their own home IoT setup, or if not, you've at least fought with maybe AC in your office. And so what you may have noticed is that unlike the IBM's marketing pamphlets, which tells about the marvelous things of smart cities, the current automated control for buildings is fairly very simple, and we can't really call it smart. And we think that before these systems can become truly smart and do interesting things, they first need to become secure, resilient, and evolvable. And today I will present you with some of the research agenda and how we think we can get there. So first of all, let me assert that what we would like to do with the systems is be able to control large portfolios of buildings with the same or even fewer amount of resources than today. But the current state of things is that we increase the scale of these building control systems, we usually get decreasing dependability. So let's just reintroduce our usual home IoT control setup. So we have some devices with sensors and actuators and a server that we usually talk to do everything. The server is very often in the cloud, although sometimes not. And what we want to do with the system is to take, well, what we would really like to do is to take a complex control policy and run it on the system for decades. While, of course, over that period of time, every single component of the system will change. It will either fail, we will want to replace it. We will also want to change what we use the system for, so the control policy will change as well. So it's kind of a ship of Theseus kind of situation. And the challenge is that, especially with the IoT style of things, the devices are often very flaky, which is why we like to send and do most of the processing on the server, which is a bit less flaky. However, the links are usually wireless, so fairly flaky as well. Now we like this setup because it's quite easy to do, but it's not resilient, it's not secure, and it's not evaluable. So why? Let's let's walk through like a very simple application as an example. So first, we just want to read some data from the sensors and send it on to the server for processing, for example, to calculate some kind of average. Based on that, the server makes a decision and sends it on as a command to a device with an actuator. Now, just to do this very simple thing, we have to transit over our flake link twice. And can't we do something at least a little bit better? So the very obvious thing that we can do is just make the devices communicate between each other. So we're kind of removing the server, not entirely, it's still very useful. We're just removing it from the critical control path. And we're making the computation we need for the processing more local, which is good, we like that. So just running quickly over our application again, we're reading on the device with the sensors. We know we want to do the actuation part on the device with the actuator, but what about the rest of our processing tasks we want to execute? Where do we put them? Now that decision we make is going to depend on a number of parameters, things like what's latency, throughput of our network, what are the current resources on our devices, and all those conditions are going to change over time. So we want to have the ability to change our mind. So like, let's keep that thought of deciding where we put our compute, like keep it in the background. First, let's just say that if we made a decision and this is what we want to do, we want to calculate the average on the device on the left and make the decision on the device on the right. Because now what we're going to encounter is reality. So with most of the smart devices on the market, we can't actually decide where we do things or how we do things. The software is very tightly coupled to the hardware. The software lives with the hardware and dies with the hardware. So the evolution of the devices and the software looks something like this, where the software evolves at approximately the same pace as the hardware. And with a new product line of hardware, we get a new product line of software. The quality of the software is often a concern. And if we're lucky, maybe sometimes we can get an update from a vendor. But we can't really specialize the development of the different components in our control policy of the control tasks that we're executing. So actually, in this case, if we did what we showed before with the application, if we were doing more things on the devices, it would make the whole situation a lot worse and make the system more unstable. So first of all, if we want better software, we need to allow it to, we wanted to allow it to become independent and to evolve if we want any semblance of security, especially. So instead of this, we want a graph that looks something like this. But this is still not enough, as I mentioned, because we want to do more things on the device. We need to allow different parts of the software to evolve independently as well, to foster something more like an ecosystem that supports evolvability of all our components over time. So coming back to our original goal, so we want to be taking a sophisticated control policy and running it on the system for decades. We want to be able to decide what software we run and where we run it. So our solution, or like how we think we could achieve this, is first of all, we take our control policy and we explicitly divide it into independent chunks of software that we then place on our devices with sensors and actuators. Now, of course, for these little software chunks, we need something to manage their life cycle, and we also need something that plums them together to facilitate communication. So that's our platform that runs on each of the devices. And then again, we would like to receive updates or new components to run on the devices. So we're still taking into consideration that we're talking to some external servers and receiving information from them. So now you say that this is quite a lot of things we want to do on a small embedded device, but most of you are probably familiar with the ESP32, which is a very cheap, quite powerful small device that has multiple cores, can have megabytes of RAM, and is not niche. It's pretty much the most popular hardware platform currently in use for smart devices in production. So this means that we can actually do interesting things. In particular, we can implement this. So I'll just take you through the architecture in a little bit more detail. So first of all, our little application control task chunks, they allow us to decouple hardware from software and allow specialization of software development for the different components, thus also accommodating multiple stakeholders and their participation in the ecosystem. And we can run them on various hardware platforms. This may make it actually feasible to make it more sense to invest more time and resources into development of software and possibly increase its quality. And this helps us with our evolvability goal. Interestingly, what we could also now do is restart the computation that runs on these devices and move it somewhere else. And possibly that could somehow help us to move towards better resilience. We'll get into more of that later. So first, what are actually our control tasks running in like what are our chunks? So if you haven't heard of WebAssembly, it's essentially an open compilation target that has been mostly used for high performance computation in the browser. But we can actually run these WebAssembly containers on an ESP32. And well, since we're kind of want to dynamically load code onto devices in an environment that is already considered very insecure, making the software sandboxed kind of helps us towards some of our security goals. And this gives us our independent portable containers. But what assembly does not give us is a system call interface. Because our containers do need to talk to the outside world, they need to talk to each other, and they also need access to hardware resources like the sensors and actuators and other things. So for this reason, we decided to make them, to interface them with the outside world via message channels. Why? Message channels give us a fairly simple restricted API, mostly consisting of put and get. And because these message channels do not live inside of the application containers, they live in the management platform. If the application dies, because the messages still exist, it's much easier to restore service. Therefore, helping us to deal with events, good things such as updates, or even bad things like crash faults, and restore service more easily and in a more timely manner. So let's just go through a life cycle of an application, the same application that we went through before. So starting with, we have some devices with sensor and an actuator, and we get our software chunks from an outside server, and we load them onto our devices. We plumb them together with message channels, and we let it run. We're very happy. And as time goes on, well, there might be some new devices with better sensors that we want to make part of our system. We want to include them, for example, to improve our measurement accuracy. So with our architecture, what we can do is just create a new data flow into one of the containers doing the processing, in this case, average, and the application can still run with more data. But what we want to do, another thing we might want to do is, because this device is more capable, we would like to actually move more of the processing onto it. So in this case, we can just move the average control task onto our new device, change the data flows to follow the new configuration, And again, our application is running hopefully with better performance than before. But oh no, we were lied to. This device is not very reliable and it died on us. Now we don't have any control tasks that does the averaging, and then hence we've lost the service. So what can we do? Well, we could ask an orchestrator for a copy of the average control task and load it up on one of the existing devices. Or possibly even the previous device has kept a copy of the binary for the average control tasks around, so it can restore it on its own. And in this manner, we can, again, restore application service. So here, using dynamic components to allow them and tolerate unreliability in the many components we're dealing with. So this is helping us towards better building systems with better resilience and evolvability. Some practical notes. So we have done some testing, but just to give you a taste of some of the results that we got. First of all, how many containers can we actually load onto an ESP32? So with a very simple application, we get about 7. Which of course is going to change depending on how complex and large your control task is. But still, this gives us some leeway to really use the capacity of the device to its fuller potential. Second of all, we're doing a lot more processing on the device. So how long does it take from when a command arrives on the device until it actually gets until it actually actuates the command on the actuator on the device? So going from a native implementation, which takes about half a millisecond, we're going to 1 millisecond, which especially in the world of building environment control, where we're usually doing things at a frequency of seconds or even minutes, this is perfectly acceptable. So we think that in order to get more secure and resilient IoT software, the software first needs to be able to outlive the hardware. How? First of all, by taking our control tasks and letting them independently evolve, deciding where and how we run the software on our system. And this gives us the ability to better respond to changes in the system. Thank you very much. And if you have any questions, please ask.
Thank you, Karolina. This was a really interesting presentation, and I see we have already a bunch of people in the queue, so please go ahead, Karsten.
Yeah, thank you. That was a pretty good lead into what I think will be part of our focus for the next 5 years or so. We already started some work on doing mobile code for IoT in the late 10s. So Klaus Hartke had his Mango virtual machine, which was essentially meant for this environment. But we didn't have the containers part. We had problems getting compilers to actually generate that code and so on. And with WebAssembly, a lot of those technical hurdles are going away. And we now also have the processors that actually allow that. So this really looks like a very bright future. And thank you for bringing this work to the T2TRG.
Thank you. I also think that because building automation is a really good environment for that, because we have that leeway with the real-time constraints not being very tight. It really allows us to build in the extra abstractions to let us be more flexible.
Yeah, there was one sentence you said at the start that got me very interested. You said, let's not do building control, let's do IoT. Which I think has made most of us smile. So when people say IoT, they actually mean home networks and probably even amateur home networks. And of course, we don't need the word IoT that much because we have our own term called Thing-to-Thing Research Group. And the thing-to-thing aspect, of course, is exactly what you are bringing. out here, that in order to get the functionality that we want from our devices, on the devices, we need mobile code, and it's like thinking of what the web would be today without JavaScript, and that's exactly where we are in the IoT, and we need to get beyond that. Thank you.
Thank you.
Hey, thanks.
Thanks
A lot for this presentation. I have one, it's a mix of a question and a pointer. When looking at this from a REST point of view, those messages look a lot like state transfers. So this is something that I think would provide a good theoretical background for work that is that's really stalled in the core working group on describing those steps where data is transferred from one hop to the next and then processed and then on to the next. So I think Dynalink would profit a lot from this background. And for the question part, like, have you looked into, do you have a model yet of how to transfer those messages? Have you looked into the core world of state transfers, or is this more on the theoretical side now and using any message transport that there is?
Yeah, so currently it's just a more theoretical of any message transfer. We're just talking simply in terms of like the managed communication, that you usually want to have unreliable or reliable delivery. So either you have some sensor data that you mainly want to be fresh, you don't care if you lose a couple of packets here and there. Or on the other hand, you're transporting like fairly important data like events or commands that can actually cause like large issues if you lose any of the packets. But yeah, I haven't really looked into co-op much and or the state transfers. So thank you for mentioning this, and I'm definitely going to look into that more.
I'll be happy to play around with this also from the co-op side. Just a brief technical curious question: when you're running WASM on devices this size, have you run into the limitation that typically there are like 64K page sizes, or is that not an issue on an ESP32 because like you just allocate a few pages of 64K memory and yeah, it's there?
Yeah, essentially that's what you do. But I think what is an issue, so in order to run the WebAssembly containers, we use an like externally developed runtime that is for embedded devices. But really, when they say embedded devices, they talk more about the larger ARM processors and boards. So ESP is really on the edge. Some of the design decisions they make are not fully suitable. So, for example, in terms of the execution and runtime environment, like everything must run in thread. Well, if we're running this on top of RTOS, which is more task-based, so there are just some design decisions that don't fully mesh nicely. So, which could be like, I would really like to look into developing a custom WASM runtime, but I don't think I will ever get there, at least within my PhD.
I might put you in contact with people who are working on something like this. Thanks a lot for the presentation. Helpful thing. I think we should have more of this in the research group.
Thank you very much.
Thank you, Chris, and thanks a lot, Karil. I fully agree there. I mean, it was a very interesting topic, and it was definitely dig deeper in the following meetings, for example, in Madrid. There's also a bunch of comments and questions on the chat that we could follow up on over there, and of course, in the future, the mailing list and in the future meetings. I still see Chris and Karsten in the queue, but are the old hands or?
No, I just put this in again. There's maybe one piece of technology that should be mentioned here that also wasn't available when Klaus did his work in 2018, which is Rust as a language. So we now have a really good ecosystem of components, Rust, LLVM, and so on, that can help us do this thing. Of course, WebAssembly is not tied to Rust, but still it's interesting to be able to use this environment. Christian, yeah, right. But I have 20 students who like Rust as well, so.
Great. So I guess we're now exactly on our timeline for the next topic. So that's, I guess, a perfect segue there. So thanks a lot, Carolina. And definitely looking forward to hear more in the Madrid meeting latest.
Thank you very much, and thank you for the questions.
Okay, so next we have then Karsten with the report from IETF 122 security discussions. Go ahead, Karsten.
Okay, so my original plan was to look at IETF 122 and do a big overview of what happened there. That doesn't quite fit to my time slot here. The security area has 32 working groups in the IETF, and I cannot really summarize all of that. So instead, I decided to actually focus on 4 groups or 5 groups. And there are a few others that also are worth a look, but maybe we can do this in the next meeting. So I can mention SCEX, which is trying to do a symmetric cryptography-based key exchange, which always was our holy grail in the 10s because it was much easier to do with the processors of the time. Okay, so what this is just looking at a few working groups. So we're talking about IETF working groups now. We are not talking about research groups. Or BOFs. BOFs are working groups that the IETF hasn't quite decided to actually start yet. And that happened in Bangkok. And look at these with very, very specific kind of glasses that look at players, objectives, and beliefs. I think you will see this set of glasses being in use in the next talk as well. Let me just try to make a few examples instead of trying to formally explain what this perspective entails. So let's look at something that may not even be something that normally would be looked at as a security thing. The SCOAN working group is doing the Tron protocol. This is about endpoints finding out what the network actually can do for them. So right now we have congestion control algorithms, but these often have a hard time finding out what kind of rate limits networks actually enforce. So there's a lot of guessing, there are packets lost, there's reduced quality of experience for the users and so on. So here the idea is that we actually have a way to get information from the path to the endpoints so they can select a data rate for sending information that actually works with what the network has to offer. So we have 2 kinds of players. We have endpoints, and because this is supposed to be a web protocol, these are now quick endpoints. And we have the network elements that are between these endpoints. And the objective is for endpoints to be able to ask the network about the rate limiting properties that are on the way. Of course, this always will be limited information because the whole network will not start to provide this information at once. But it's good to have a protocol that we can point to and move forward. The protocol actually is surprisingly simple because it can make the assumption that we are using quick for the actual data. So the protocol works by the source endpoint putting in an unprotected Tron packet together with quick packets and coalescing all those into a single datagram. And the receiving endpoint looks at this packet and can be sure that this packet isn't entirely forged because it has quick packets in it that are protected. So the endpoint is kind of certain that the packet is for real. It doesn't know if the Tron information in the packet is right. But here the observation is those network elements that actually can modify the Tron information already have full control over your data. So they can do rate limiting And the only thing that might be a problem here is that they might be lying about rate limiting, and that's of course very hard to fix without getting some authentication and actually responsibilities for things and so on. So that's not what they try. They just assume network elements that are on the way, that are doing the rate limiting, also can patch those unprotected parts of the coalesced packet and put rate limiting information there as well. So the belief is, because the packet that came in had working quick components, it must be a real packet from the source endpoint, and it must have reached the receiving endpoint over the path that actually we are trying to ask for its status. So it's a pretty well protected packet, even if the actual information is completely unprotected. So the document has this little picture which explains the players, the sender, the network element, and the receiver. Of course, there can be many network elements, and the network element modifies the empty drone packet into one where rate limiting information is added, and the receiver validates this by validating the quick packets and not by trying to validate the drone packets, which it cannot. So that's pretty interesting from the point of view of looking at the players. What can they do? What do others think about those components, those players, and what beliefs can we actually derive from that? So I think that's a very nice example for things we also could do in the constraint space, where we, of course, can add information to OSCOR, which has a much more fine-grained way to handle protected and unprotected information. So just as a little spark to start thinking about. The second event I want to talk about was the Nether-BOF, and that was very controversial, which is not the part that I'm interested in here. But they had an architecture, and let's talk about the architecture, and let's not talk about whether we think we actually need this or know how to do this. So the idea is that we need a way to actually ensure that packets take a path with certain security objectives. And one point of contention is, what are those security objectives? The most important thing that people have in mind is that the routers, the network elements on the way, all are not compromised. So we are getting information about that by having them a test, and having some component actually at the end looking at the attestation evidence. So this is the picture in the document that tells you a relying party motivates an orchestrator to send in path evidence. This takes the route, the actual packets are taking the path evidence, is collected on the way, and it's looked at by a verifier at the end. This is just one such picture. Look into the document for alternative ways of doing this. But again, we have different roles here. We have pieces of protocols that we already have, like doing attestations. And the question is, how do we piece this together into something that actually creates value? Third example, the selective disclosure protocols that are being done in OAuth for JSON and in SPICE for CBOR. These are based on a model that has three kinds of players: an issuer, a holder, and a verifier. So the issuer is our garden variety issuer that tells something in a signed statement that contains some claims. That is the information we want to be able to give to somebody else. Like my university actually hands out diploma documents that have claims about students, like they are now masters in computer science. Of course, we want to be able to make these documents available at some point in a digital form. The second party is the holder of this credential, which would be the student that just got a master degree. And the student, of course, wants to be able to put in this credential into, for instance, a job offer and during hiring discussions and so on. So the holder of the credential, which we could also say the owner, which is just a bit weird because the issuer is an owner in a different sense, that can present the claims that it got signed by the university to a potential employer. And the verifier, actually, we would normally say relying party, but for some reason this is called verifier, which is conflicting with RED's attestation use of this term. So the relying party can look at what the holder presented and can verify that. And going beyond that, this authentication, there is an authentication that actually allows the verifier to verify that it was the holder that actually submitted that and not somebody else. Okay, so this all more or less works, but the new objective is to let the holder be selective which claims it actually discloses. And there is a protocol. I'm not going to go into details, but the idea is that in the middle of this picture, there is an opportunity for the holder to actually redact claims. So my diploma contains a lot of information, including actually individual grades for individual classes. And maybe I don't want to tell my employer my grades in theoretical computer science, because if they see them, they will immediately think I'm overqualified. So I have to redact these claims so that they actually consider hiring. So that's new. That's new in the picture. And what the document now does is go into details how this actually would work. So what interchanges are necessary and what are the beliefs these interchanges provide to the various parties. So one element here is to have selective disclosure token and then build a presentation token, which is called SDKBT for the SOD-COT SDCWT approach. And that is actually what the holder hands to the verifier. So it processes the issuer's information into something that the verifier can use. Yeah, so there is some redacting going on, which requires a few cryptographic tricks. And then we have issues like linkability. We have to look at if you actually want to ensure that there's no way to actually stitch together information from multiple of such statements and get more information than you actually should be getting. So again, we have a very clear view of what are the players, what are they doing, what beliefs are they actually doing. Yeah, Michael has more details. I don't really have time to go into the details. Yeah, I also think that SDCWT is a little bit nicer in many ways. Anyway, so let's look at the last one I want to talk about, which is called SCIT, Supply Chain Integrity, Transparency, and Trust. This is really biting off a very big chunk of our economy about suppliers making statements and making sure that these statements actually are transparent, at least to those who should know about them. They may be totally secret to others. And we have a lot of roles here. We have issuers, we have subjects, which may be the issuers themselves, or maybe the clients, which may be devices or actually digital objects, artifacts. And we have a transparency server, which is really the big new player here, which takes registrations and puts them into an append-only log, implementing a registration policy and issuing receipts. And the receipts are the cryptographical component that holds all this together. And what's really interesting about SCID is the complexity of the problem that is being solved and the relative simplicity of the cryptographic components that are needed to piece together the solution to those objectives. Okay, we have another one of these pictures, and it takes a little bit longer to look at that. I just want to motivate you to look at documents like these and try to understand what are the various roles here. Are maybe some of the roles the players have ones we would find in an IoT environment? Do these protocols work in those environments? Do we maybe need to modify them a little bit? This is maybe something that is a useful approach for future work in this research group. So that's all I wanted to say. And I'm seeing a great discussion about Nether in the chat, which I'm hoping we are not getting into here because of all the controversy. But do you have questions?
Yes, thank you, Carsten. I think we have a time for a very quick question, if anyone has, although there's plenty of questions and comments in the chat already. Anyone wants to still jump for the mic with one of the questions? Or we can continue on the chat and of course in the mailing list after the meeting. But thanks a lot, Carsten. Very, very nice overview of the work progress in the IETF side. So with that, next is Mohit with the update from the draft.
Hello. I guess good evening for most of you, maybe good morning or afternoon for others. So, yeah, I guess this is a update for the draft on terminology and processes for initial security setup of IoT devices. It's been a while since we had an update, so just a quick recap for those who don't know what this draft is about. So at some point a few years ago, we started seeing a lot of protocols for doing this initial set of actions to set up an IoT device and get it operational. And there are like a lot of different terms used for these. So we started like looking at these protocols and thinking, do they do the same things? Are they trying to achieve the same goals? And how are they using different terms like bootstrapping, onboarding, provisioning, enrollment, commissioning? So we thought it would be a good idea to at least capture these terms and see how different standards, both IETF standards and also standards that are developed outside the IETF, how they are using these terms, what are the commonalities, differences, if any. So that was the initial goal, to see if there are differences in how these terminologies are being used. Are there some, let's say, even differences in starting assumptions of different protocols? I will have a list of protocols in the subsequent slides. But before we go to them, we also wanted to compare, like, do these protocols all have the same initial assumptions, or do they have some different assumptions about the IoT device? So for example, many of them assume that there will be some kind of certificate that is installed by the manufacturer of the device, and it will be used for this initial set of actions that need to be performed before the device is up and operational and performing the task for which it was purchased by the owner of the device. So that is one thing on which we want to look, compare different protocols. What's the initial assumption? Okay, then what happens after you run the protocol? So the device is the end goal of all the protocols is that the device should be operational, but in order to be operational, it, I guess, gets some extra piece of information, some kind of configuration file, IP address, perhaps if it didn't already have one, some new certificates, some information about new servers that it should contact, etc. And here I've used SZTP, which is secure zero touch provisioning, as one example, but obviously different protocols will have different initial assumptions, and then once the protocol is run, the information that is installed or configured on the device will also vary. And then we also wanted to look, okay, who are the players involved in these different protocols for getting the IoT devices up and running. And when we say players, we don't necessarily mean like players like client, server, devices, um, some kind of provisioning servers, Masas in Brewski, and so on. I mean, there might be lots of components, but we want to look at a slightly higher level of players. I would not like to say human, but um, let's say we don't want to list when looking at players about the endpoints participating in the protocol, but okay, what is the role of the device manufacturer? What is the role of the device owner? What is the role of the end user? And sometimes the owner of the device might also be the end user, but sometimes it might be different. So someone might own a network and own a bunch of devices, but the end users might be different, and there might be different actions required by the owner, by the end user, by the manufacturer. Often, if protocol expects that there will be some certificates, the manufacturer will need to have like a hopefully some secure factory processes where it can install these X509 certificates. Some protocols even assume that manufacturers will also provide additional services, run some servers, do some asset tracking, and SZTP, for example, is one of them, where the manufacturer not only installs certificates but also has to do additional things. And this is what we want to then compare. Who are the players involved? Is there some requirements from the device manufacturer? Is there some requirement from the owner? And then how are they involved? It can be that, okay, the manufacturer just needs to install the certificate and the owner needs to scan a QR code, or does the owner need to do more? Does he need to set up some servers in his or her network, and so on? So quite a ambitious target, and there are many protocols available for us to look at. So obviously, from the beginning, our goal was not to be exhaustive, but try to, let's say, collect a list of illustrative protocols which are like different enough in unique ways, so that they provide like as exhaustive coverage as possible. Of course, there will be other protocols that are not listed in the draft or on these slides, but I think like this list we are mostly happy with. Of course, if you think there is something additional that should be added, we can consider it, but this is more or less now the stable list of protocols we are trying to cover in the draft. So we are trying to go through each of these, identify what are the initial assumptions, what are the information then configured on the device after each of these protocol is run, and who are the players and how are the players involved. Obviously, you can imagine there's 11 standards, and some of these standards documents are hundreds of pages long. So this is like quite laborious work, and that's why it has possibly been a little bit slower than any of us would want, including the authors. But we seem to be making progress. So what has happened in the last couple of versions? So we updated some of these protocol descriptions. So I have here example of SZTP, since this is one of the protocol where the description has been updated since the previous versions of the draft. So in the earlier version, we were just listing a bunch of terms that are being used in the standard, but not providing context. Okay, how are these terms being used? And I think that was kind of important to also provide context in how those terms are being used. Otherwise, it's just like, anyone can open the standard document and find for those words and then say, okay, these words exist and these words don't exist. But that doesn't provide any context to the reader. So what we are now trying to do is also provide, okay, in what context is that word being used for? So for example, why I took SZTP, that it uses the word enrollment, but here it's not enrollment of devices, um, which is what you would expect if you know EST, enrollment over secure transport. Here it's like enrollment of the device owner in the manufacturer's SZTP program. So basically manufacturers have a program where they will enroll the owners, and this has nothing to do with the devices which will eventually be shipped to the owners. And this is where the device owners will tell, okay, here is my ownership voucher, certificates, please send me 10 devices. And then the manufacturer will record, okay, here is the serial number of those 10 devices that are shipped to you, and you can then bootstrap them or onboard them into your network. Of course, I can't go into explanation of how SZTP or Secure Zero Touch Provisioning works in this presentation, but I think if you read the draft, it has a sufficiently good summary to get an overview of how the protocol works and how each of these terms are used. So that's change that we are doing basically for all the protocols, not just listing the terms, but also telling how the terms are used. Then for players, again, as I said, we don't want to cover that, okay, there is some server, there is some onboarding server, there is some bootstrap server, there is some client, there is some device, there is an administrator. Maybe administrator is a relevant player, a network administrator, a manufacturer, a device owner, a device user. So we are updating each of the protocol to not list the protocol endpoints of servers, devices, clients, but rather who are the players like manufacturer, owner, network administrator. This is again change we are gradually making to each of the protocols in the draft that we are covering. So what's the state so far? I guess 4 out of the 11 we feel ready to be reviewed. Please read the latest version of the draft, specifically these protocol descriptions and the description of how they use the various terms, which players are involved, and we look forward to early feedback if we are at least on the right direction with this approach or not. And I will try to do better, and together with my co-authors then finish up the other 7 protocols that have not been updated with this new approach. And finally, when we are done with all these protocol descriptions for each of the standards, we intend to have an updated comparison section. I don't think we can do a fair comparison until all the protocol descriptions are something which we are satisfied with. Hopefully that comparison section would be relatively easy once the protocol descriptions are ready and something which we are happy with. I apologize to the group that progress has been slow, both because of professional and personal reasons, but we'll try to do better in the coming weeks and months. So that's it. This was my last slide. Any questions?
Thanks a lot, Mohit. Glad to see this moving forward. We're a bit over time, but if there's some quick questions, anyone want to jump on the mic? And I see Michael Rich already proposed to schedule a design team meeting to progress more text. I think that would actually make a lot of sense. And also for the reviews, if we should reach out to the specific organizations or people participating there to get their views. Maybe that's something we could look at, and let us know if you need help from us chairs to facilitate that.
Sure. I guess so far we have mostly covered the IETF protocols, SZTP, EST, EFP noob, but yeah, I guess we can find some colleagues to help us, do a quick read and let us know if you're on the right path. And this design team idea also sounds great, Michael. Thanks for volunteering to help.
Very good. Thanks, Mohit, and thanks a lot, Michael.
Thank you.
Okay, now a bit behind the schedule. Next up, we have Michael Richardson. Please go ahead.
Okay, and do I get slide control? Do I have slide control? Oh,
now you do.
Oh, now I'm supposed to pick my presentation. I'm confused by this.
Sorry.
Oh, I think you pressed the wrong button here. Let me just yank control. Do this again.
Okay, and now you need to give me.
Yeah, it's
so
annoying that it always asks whether you really mean what you just told it to do.
Right.
Yeah.
Wait, so my apologies for I'm in a bagel shop because I had a last minute schedule change to specialist that I see. So my apologies for the noise. Like Mohit's document, this one's been sitting around for a long time, and I'm just going to recap very quickly why it's been written, because I think that's as useful a thing to understand. There's only 9 of us here, which is unfortunate. But basically, when we were doing Brewski, one of the pushbacks, and a number of other protocols as well, was, oh, well, manufacturers will never possibly keep their private keys private. We can't trust any of this stuff going on. And there's some real cases in the field, like the situation in Taiwan, which was brought up again, I think, last week at one meeting. If you haven't read that paper, it's truly astonishing that's what happened. But anyway, and to unfortunately, the terrible line, not all men, but not all manufacturers are as bad as the other ones. And so the question is, come back and say, well, how can we tell which ones are good and which ones are bad? And it's hard to tell because there's many NDAs involved. And even if it's even if you're in that supply chain somewhere, if it's 2 layers away of supply chain, then you don't have the NDA to actually collect the information that you want. And so, the story is, the story about the different blind people who are examining what turns out to be an elephant, but since they're actually examining different parts of the elephant, they don't actually conclude it's an elephant. They just see little bit parts of things, and that's because of the non-disclosure agreement. And so the goal here is that, well, you're going to have to engage an auditor, and there's an ISO 17001, et cetera, 27001, which it turns out not to be about PKIs at all. It's about how you do an audit. There's no crypto part at all, but it turns out to be the right ISO process for doing this. So the question is now, what can we come up with a set of normative descriptions that an auditor can come back with and say they said they were doing this, and they'll have some terminology, and we confirm they are actually doing that thing that they said they're doing. And so your trust in the process can be elevated there. And it might be that you discover that product XYZ is perfectly good for running your thermostat in your home, but you would not want it to be running traffic lights, okay? Even though maybe it's exactly the same kind of thing with just a different WASM load, but the base system is not secure. So what is it about? So the document so far, so it's gone through a bunch of things. It's grown a number of things. It's the table of contents. It's a taxonomy. When it moved from SecDispatch into T2TRG, the word taxonomy came along, and some other things about this. So specifically, for instance, an IDEV ID. What is it? Where do we do? How do we generate it? And things like that. And so, for instance, one of the things that I struggled with in a couple different places was There's several different ways of generating a private key, and we even have this in some of the EST protocols where you can generate the private key, in the device, and you generate a CSR, you send it to the factory, and you get a certificate returned to the device. So it involves a one round trip off the device back to the device. And then you could generate the key in the factory. And that's an interesting thing because some devices have terrible random number generators. And so the factory generates the key, it generates the CSR, gets signed, and then as a single trip, you load it into the device, probably through a bed of nails test, but there may be some other different ways of doing this. There's a third way that the document comes up, which is that you have a preloaded seed, and you generate the private key in the device from the seed, and you generate the key in the factory from the seed. The factory throws away the private key after generating the CSR, and then you load that together up. And then you have the same thing, but now actually the device is not doing it, but rather you bought a secure element, which is basically a device a bit like a TPM, but without all the functionality, that basically can do some things, and you can get them loaded with private keys. And either the CSR was generated in a secure element, or the CSR is generated in the factory. What are these strange names? Well, we started with ABC. They seem really non-intuitive. I said, well, let's put some other names attached to them. I'm not attached to them. It's quite whimsical. Not everyone likes my level of whimsy, but that's where it came from. Some of this went into a recent NIST document involving IoT onboarding. I did not like my choice of terms, so they have method 1, 2, 3, 4, 5 in a slightly different order, but the descriptions are essentially the same. If you have a better idea, or you really hate these words, or you would prefer different words, or just go to ABC, then that's the kind of conversation I really do want a bike shed on the list, because I think that it's a useful thing to say. If I told you it's method A, you'd be just like, what? I have to go look at my card, but maybe you would get it if something else happened. So that's one of the kind of controversies that I would suggest that is worth having and worth discussing. But are there more than 5? Maybe there are more than 5. And Carson says, yeah, broccoli. You want to have a consistent naming system, then let's go for it. There's a bunch of other things that in this document that we've discussed before. Behind you, chocolate. Yeah, there you go. So as I said, please post all of the suggestions. I'm open to anything. I just want something that's recognizable and people will ideally is mnemonic in some way. Any questions? I have a couple backup slides we can, if we need them.
Thank you, Michael. Unfortunately, I don't have good names, but looking forward to have more. Would actually love to hear from the NIST discussion on the method 1 to 5. Like, was there any good proposals there?
No, they had no good proposals. We had a lot of conversation about even getting to the 5 and not 12. I would say about that, and saying no, that's just a variation of method B. No, that's another variation of method B. Well, that's kind of thing. And then the fact that 2 separate methods were identified for a secure element, which is essentially methods A and B, but outsourced to a previous stage of the manufacturer for that. And I'll also just say that there's developing the next week or so, there'll be an announcement about a device identity forum, which will deal a lot with what of this and the marketing of it and the propagation of the actual techniques. So that's happening through the IETF, and it's kind of soft launching next week sometime. So we'll see how that works. Any other questions? Mohit.
Yeah, I don't know how to now join the queue, but I can unmute and just ask. So, like if maybe okay, I think I understood that the goal of this document is to help auditors who visit factories to make sure that they are discussing the same things when talking about how keys are being provisioned.
So auditors do visit factories today. Manufacturers and various levels will have their process audited, various levels of degree. Those audit reports tend to remain confidential, which is useless for 2 layers down the supply chain, right? They want to know, what exactly did you do? What did you find out? And so this is the goal, is these are a set of terms which they would be willing to publish. So for instance, one of the terms that I removed was perhaps you're familiar with the bus count of a project, right? Which is how many people can be killed, or another version of it, can win the lottery before your project is dead. You've lost enough people. And so it turns out, if you're doing secret sharing for your PKI route, then the question is, how many of those shares can you lose before you have a problem? So that count is probably something you can make public. But whether that's 5 of 7 or 9 of 11 that you must have, that's probably not something you need to know, right? And outside of the organization, you just need to say, okay, so how much redundancy did they really have? We went through this, we saw this with the DNS route. They could not have a key in 2020, 2021, they could not have a key signing ceremony as they normally did. They did something weird. They wound up, basically drilling the smart cards out of the safe, which they couldn't open because they didn't have all the people, and they had safe issues. But they adapted their process such that it worked, even though they couldn't get people together physically. And that was audited in the sense that it was all recorded and made visible to the public. But there's quite a few entities where they, discovered, well, they have 2 shares in Australia, and 1 share in North America, and 2 shares in China, and they need 3 shares to renew their thing. So, but nobody could travel. So what do? Right? And so that's one of the questions, like that could screw up your supply chain seriously if we had another pandemic or other travel restrictions. Then, well, it would be good to know what their level of redundancy is for that.
Very, very good. Thanks a lot, Michael. Unfortunately, we need to maybe continue the discussion on the mailing list, and perhaps in the Madrid meeting, especially on the naming. That sounds like a good face-to-face exercise.
Well, I would love for it to happen beforehand. I don't think we should wait that long. So please post. I think there's not a lot left to do. I would say let's just do this on a mailing list if we can do that. That would be wonderful.
Sounds like a good plan then. So please post your suggestions and discussion on the mailing list then. Okay, and then finally, Christian Amsusen, go ahead with the rate time.
Hello. Yep, I'd like to talk briefly about rate time. So the challenge around this that I've met time and again with customers talking about how certificates can be used on a long-term basis is that there are IoT devices that can just be intermittently powered and might not even manage to have a clock running. At the same time, when you then finally have the device running again and get there, you might not be in a position to have a full round trip back to any service that this server trusts. So this IoT device, this server, could have been sleeping for forever, and it just can't tell. My expectation was that the dilemma is kind of known in literature, that you have the choice to either fail safe, but fail the operation and require a round trip, which could be a literal round trip, like walking off the mountain back into where you have cellular reception, and then back in to return the response to some challenge, or to tolerate that tokens are expired and that this has consequences. Turned out I found no discussion of that topic, so I thought, like, okay, that's research that has apparently not been done, or at least not written down, so let's do this here. To get these things done, I basically did 3 things in this document: explore alternatives, and brief spoiler, there is not really any. There's like, people keep coming back to ideas like, yeah, maybe ask GPS, but no, that's cheap to spoof. Maybe do certificate revocation. Yeah, that's just amounts to the same thing as having a time synchronization step. So it's really like a matter of trade-offs, but these trade-offs need to be explained, and that is what is happening in this document. There are open questions in this document that are not so much on the research, but on the technical side, because eventually I think that this should be addressed, be practically addressable in the ACE framework. So there's the question of like how precisely to do this. And that standardization work, so that does not fit into a research group. And sorry for using the term working group here. It's, of course, a research group. But to do this, I think we'll need to have the background terminology, and yeah, this can happen here. I presented this about like 1.5 years ago or so and got some good feedback that also wound up in the latest version of the document, including earlier work that was somewhat done, but then later removed from an Anima document. And I think the research group was kind of happy with having this here. My work there is ongoing, also in that I'm working on a practical implementation as part of ArielOS. That's unfortunately not in a state where I can say that I have one yet, but that is going to change soon. Nonetheless, I'm soliciting input from this working group as to how this document can progress here, whether this is still something that you want to have work done on, and whether you have found any more pointers that I could work in as background reference, or maybe even want to contribute here. That was way shorter, I think, than we planned, but nonetheless, I think it covers the whole situation. So any questions, pointers, comments? Carsten?
Yeah, I think that this whole area is a nice example of the engineers' mantra: if you don't like the solution, change the problem. We have a problem here that has been demonstrated as unsolvable. So we actually have to modify the problem. We have to talk about what actually are the objectives that we want to achieve. We cannot achieve all of them. So how can we actually relax these objectives to get something that's workable? It was really interesting to see the last 5 years where the TLS working group tried to grapple with the encrypted SNI problem, which is not a problem that you fully can solve. So they also went through a number of approaches and even threw away a whole working deployed design because they had a better idea at some point. And I think this is the kind of discussion that needs to be done here. And of course, this needs to be discussed also with a strong view to what is the deployment economy? Are people going to do that? What is the benefit they get from that? So I would be really interested in making some progress on this.
Thank you.
Yeah, maybe I should just add one point. We had the discussion in the chat about the safe that needed to be drilled. I think that's actually an important part of any real-world solution to find out what's your backup strategy. Can you do something on the real-world side that can get you out of a problem that you are having? How do you make sure that you only have that when it is fully audited? There are some YouTube videos about 24 hours of safe drilling, which of course could be faked in some way, at least today with generative AI. But there was some auditing going on there, what are the standard ways of running into exceptions and handling those exceptions? Because we tend to design systems for the cases where they work, and unfortunately they don't always do that.
Since we still have time, isn't it now like common for some companies to just use whatever cloud HSM offerings there are from the popular cloud providers rather than building this Shamir secret sharing themselves? There is like all kinds of private CA offerings, and then you outsource the problem to someone else to make sure there is geographical backups and availability and so on.
Last time I looked, some of these solutions were exceptionally expensive, like $400 per certificate for IoT device, for example. But they run everything for you. So that was like, I was like, wait a minute, did you get a decimal point wrong? Okay, because I was thinking 40 cents, and the answer was they were not. But you know, some of this just we have a market mismatch for what people are willing to pay and what it really costs to run some of the stuff, I think.
Yeah, we all remember the time when we knew that a certificate would cost us $100 per year. And it took some effort to actually change that. And of course, the Let's Encrypt project in the end was the one that changed the market realities here. I think it's really interesting to look at this again from players' objectives, beliefs, and point of view. Sometimes you actually have to invent the right player. So the SCID people try to solve their problem in a technical way, and at some point they decided that doesn't work. We actually need a player here that has a certain commercial objective that makes that player work. And that was the transparency service. So the transparency service is designed in such a way that you can have competing suppliers of this service and are in a situation where, of course, you would probably try to choose one that you can pay for, but you also want to choose one that has at least a certain amount of stability and reliability and so on. And that's exactly the kind of component that we need competition for to actually make work. So that's probably a strong direction of thinking. So how could certain aspects of running a company that produces IoT devices, how could those make use of services like this transparency service in a way that helps us fulfill objectives?
Yes, thank you for the good discussion here. One more question, actually, to you, Chris, on the rate time. So, did you look at 3GPP networks as a potential source of timing data?
Yeah, 3GPP networks are a potential source of timing network of timing. But once you have connection to them, you have connection to the rest of your internet, and you're not in an offline situation anymore. This is really about situations where you do not have that. When you're deep underground, when you're somewhere in the mountains, when you're at any point where you don't have that kind of connectivity, either because that service is not there or because your device is not equipped to talk to that service. So maybe there is now no point on Earth anymore where you can't get a satellite uplink, but that still means you need to have the radio to do that satellite uplink. So maybe at the point when like Tesla's promise of the fully electrified atmosphere comes true, we won't need this anymore. But until we have that prevalence of communication and energy everywhere, I think we will need something like this. Yeah, sure. 3GPP, when it's there, fine, take it, talk to it. And I did not explore like how trustworthy any particular participant's data then is. But it's a different problem then.
Because that's what I think, like the trustworthiness at least is better than compared to the GNSS solutions, etc. But anyway, very good point. There are definitely a lot of situations where you don't have that available, so you still need additional solutions. Thanks. Okay, then we are approaching the wrap-up part of the session. Any more questions or comments on any of the presentations? And I see we still have a lively discussion going on the chat. That's great, and we can of course continue the discussion, especially on the mailing list going forward. So if there are no other questions or comments for now, I thank you everyone for joining the discussion presentations today. And we will have, as just discussed, most likely one more interim meeting before summer, and definitely looking forward to see many of you at the face-to-face meeting in Madrid. And meanwhile, let's continue the discussion on the mailing list. Thank you everyone, and talk to you soon again.
Thank
Thanks.
you.
Have a nice day.
Thank you, everyone.